Well, welcome back, folks. Looks like we can get started. So for today's class, we're going to just be moving forward through chapter 14. We have two examples left we're going to get through in the notes. We started a little bit example 4, but that was just looking at the context, writing down the parameter value. And we're about to go through the mechanics of the rest of the confidence interval we have described here. But for the other major announcement is we're getting closer and closer to our upcoming third exam. This is it for the 75-minute exams. After this one, the last one on the table is just the final exam. The final exam is going to be a comprehensive one, and the only chapters it'll miss is chapter 14 and chapter 15. Doesn't mean I'm going to emphasize those chapters. Doesn't mean there's going to be a bunch of problems from those last two chapters. The final exam is going to be comprehensive, giving the entire class about the equal weight. So you might expect one problem from chapter 4, one problem from chapter 15 at the maximum on the final exam. But as far as the third exam goes, it's going up to chapter 13, so that makes quiz 9 a really pivotal quiz. I'm going to try to grade these early. A lot of people have turned them in early already, so I'll try to get some of these graded, handed back on Thursday's class for the folks that have handed them in early. If for some reason I don't quite get that done, I'll be emailing them back to you on Friday, as I typically did with the other exams. So best way to study for upcoming exam 3 is work through your quizzes related to these 3 sections. That was quiz 7, quiz 8, and the quiz 9 that's due tomorrow. Those would be great sections to take a look into. Next thing you might want to look into is getting caught up on the MyLab statistics homework. Those problems are sometimes a little bit different, a little bit tougher, but spending some time there is doing double duty. It's getting your homework score up and getting you more familiar with those concepts. Then the next thing you'd want to take a look into is the sample exams versions 1 and 2. But maybe before doing any of that, a good starting point is putting together your set of notes for the third exam. And it's really just our third go at this. So the same kind of routine you got into on getting prepared for exam 1, putting those notes together, and then exam 2, we're just doing all over again. So you'll have a single page of notes available front and back of this size here, or smaller, but this is the maximum size, just ordinary letter size. And also, when we come back on next class, very first thing we'll do is just go over some brief announcements, some reminders about the upcoming exam 3, and then I'll turn it over to the class like we did on the other exams, calling for review questions. If we're not sure where to start, I'll make sure to pose one myself, so we'll at least do one question for sure. And then it's all up to us on how many questions we want to take a look into thereafter. Version 1 of the sample exam is, let me remind myself, new problems, it looks like for chapter 7, chapter 10, and new problems for chapter 13 as well. So if you want fresh problems, this is where you'll find them in version 1. Version 2 is just the lecture notes. But the lecture notes becomes noisy after we've completed them. They're hard to look at again, the full solutions. So if you want to run through the lecture notes again in a clean form and see what exactly qualifies as a good exam question, these are good ones to look into. There's no formulas or definitions here to get you distracted. It's just the pure questions, the way they would have looked as actual exam questions. So either one of these versions would be good problems to take a look at on tomorrow's review, or really anything else, whether it's a quiz problem, a totally unrelated problem, a problem in MyLab statistics, in the Axis Pearson thing right here. I'd be happy to discuss anything. So that's where we're at so far, folks. Any questions at all about any of those announcements? Okay, and maybe one thing to mention, because this one didn't really fit the pattern of what we did on the last exams. This exam ends at chapter 13. We might have fit in chapter 14, but that was a tight squeeze. And these chapters are pretty dense with what we're doing in there. That means quiz 10 is kind of an odd one out. It's due on November 20th, a week away from tomorrow. Because it's based off chapter 14, you have a ways to kind of strategize here. If you want to just leave this on the table for after Monday's exam, that would make sense for some people. That way you're going to focus on just the exam concepts, 7, 10, 13. If you want to get it squared away and early and done, then that might be the best strategy for you as well. If you just want to get all your thoughts on paper, and it is another conference interval problem, but slightly different methods. Just know as a reminder, because this is different this time, the quiz 10 chapter 14 problem is not on the third exam. So we're not going to use this formula here. We'll be using the chapter 13 formulas. But I think that's it for the announcements today. That was 5 minutes of straight talking. Any last questions at all before we get started? Okay, let's jump back in then. Chapter 14, we got to the good stuff doing the confidence interval problems, and we solved one already. So here's the second context we're looking into. The reminder is the random sample is based off 21 people who have early onset of dementia. The actual data itself is the age of diagnosis, making this a quantitative variable. The very first thing we had to do with this data is import it into the calculator and compute out the summary statistics that we see here. After that, we wrote out the parameter is going to be the population average, age at diagnosis, because that's what the data reflects for the quantitative variable. And we said for all people with early onset of dementia, we were particular by saying diagnosed with that particular condition. It's kind of said once already when we said age at diagnosis. It kind of implies the population is people with that are diagnosed. But we decided to be really specific in putting this in. So now that we have the parameter down, this is kind of the mathy part of it, putting down formulas, doing computations, making substitutions. But any questions with the refresher on this problem? Okay, well, let's run through the portions. For the standard error, the sample mean, we're going to compute this formula. The way it looks is by symbols, SE for standard error of y bar, and by formula, it's just the sample standard deviation S divided by the square root of the sample size n. So it's a great formula, a little bit more complicated in chapter 13, so we'll definitely review at least one of those problems tomorrow. S is 6.4701 divided by its square root of sample size, which is 21. And this is what we're going to get out of it. To 4 decimal places, we'll round. 6.4701 division by, that was a mistake. Let me backtrack that. 6.4701, shouldn't have hit the clear button. Divide by, I think I hit up arrow instead. Hit second button, power 2 to call the square root, and throw in 21. So rounded to 4 decimal places, the standard error is approximately 1.4119. Now that we've got that in play, the last thing we need to do the full confidence interval is just the critical number T star. This one we do from scratch each and every time, like we mentioned. And we really start with the level of confidence we're dealing with. If confidence is at 99%, the very first thing you want to do to that is convert it into a decimal number. So C is 0.99. And to get the critical number T star, we have to tell the calculator what the area is going to be. So this tells us the area. It's 0.05, but really sometimes it's just convenient to leave it in the calculator like this. 1 minus 0.99 divided by 2 gives us the right left-tailed area each and every time. We'll get a negative critical number like before, but we'll just convert it to positive. Other thing we'll need is, it's not just about the area, we also need degrees of freedom. We wrote that in as df, formula is n minus 1. So throw in the sample size from up here, it's going to be 21 minus 1. So degrees of freedom in this problem is 20. Next thing we do is we use the inverse. I think I remember making a mistake here and called this inverse norm. This is the inverse t distribution. That's a giveaway. If we're going for T star, it's telling you which distribution to use, the T one. T distribution just needs this area, and this degrees of freedom, 20. So we access that by second vars, just like with the normal distribution. Go down to option number 4 for inverse T. Area, we kind of already have the structure here. 1 minus, update to 0.99. 99 on this one. Degrees of freedom is one less than sample size. So in this problem, it's size 20. And this is what's going into the calculator. Basically, the same exact thing we have down on paper. So hit enter on all that. Give the calculator a moment to think about it. And we've got a T star set equal to 2.8453. So to me, I think that's the weirdest part of the entire process. I think that's where I made the most mistakes on the notes. Any questions at all about getting that pattern down to getting that T star so far? Awesome. Like a lot of things in this class, it's just kind of a routine that you get used to going through just through practice. You'll see this problem again as a final exam problem, and you could just scour these examples just to remind yourself what you're doing. You definitely want to remind yourself on getting area, degrees of freedom. You could put on your notes, hit second vars, go to inverse T, and then you'll have all your bases covered for getting that critical number out. Last thing is just to put the whole confidence interval together. Formula you would need for this one is going to be y bar. Let me get my colors going. Y bar add or subtract that critical number we just computed, T star, here it is, multiplied by standard error of y bar. We mentioned this before. This is kind of like doing the 1.5 IQR rule of thumb. It's a totally different formula, but it's the same kind of substitutions you're making. Instead of a quartile 1 in an interquartile range, you just happen to be plugging in the sample mean y bar instead this time. So throw in that value, 52.5238. Add or subtract that critical number, 2.8453, that came from the 99% confidence, and then multiply the whole thing by standard error, 1.4119. That's the whole interval. So if you've got that on paper, you basically have the whole problem. You might lose a half a point at worst if there's a calculator mistake that we made, but you're not going to get docked for it again on part E. Any questions bring it all together to this stage? Okay, our big punchline is we're solving for mu. It's placed in the middle, and this whole procedure is basically casting a net. Y bar is just like a precision shot. We're estimating mu with one specific number, and there's no guarantee that's right. It's almost guaranteed to be wrong. The sample mean is not necessarily equal to the parameter unless you took a complete census. When you do the confidence interval procedure, you're combining the margin of error and estimating the unknown mu with y bar. This margin of error is wide because we're using T star. And again, it's like casting a net to try to capture something unknown. And the success rate for our capture is high, 99% chance that the interval we're about to produce will contain that unknown population parameter. So let's dump it into the calculator in the next step. 52.5238. Do the lower value minus 2.8453 times 1.4119. And there it is for the lower bound. We're rounding these values to 2 decimal places. And recall that these data were age in years at diagnosis. That's what our sample mean and sample standard deviation actually represents. So let's put that in our answer as part of the units. 48.51 years. For the lower bound, and you probably already know by muscle memory the standard trick. We've used this a lot. For the sake of accuracy, most of all, but also speed as a side benefit, use up arrow and left arrow just to flip over this sign to positive, and now you have the upper value. So upper bound of the confidence interval is 56.54 years. And it's a scary problem because remember, this is about early onset of the most devastating condition ever in some sense. Well, there's lots of devastating conditions. This one's just a bad one, early onset of dementia. We're saying that for everybody with a diagnosis that suffers from this condition, we think their average age of diagnosis is between as early as 48 and a half years old to about 56 and a half years old. That's a pretty big width to our interval. But remember, the sample size was kind of small. There's just 21 people in this study. That's one reason the interval is so wide. But it's also wide because we're going for a high level of confidence. We want to make sure we consider as much possibility for accuracy as possible with that high level of confidence. And so that's why the interval here is so wide. Next thing we'll do is just interpret this interval. Let's mention the margin of error just one more time. We mentioned it's not a question I ask a lot on quizzes or exams, but it is a question that is like a concept question in the homework that does come up just occasionally, not every single time as well. So one last concept. If you put this together, those two parts right here is the margin of error. It's the stuff that you added and subtracted to the sample mean to build out the whole interval itself. As a formula, it's m equals t star times standard error of y bar. So again, just these two parts right here form the margin of error. So that means in our problem, to calculate it, fastest way is up arrow again, and go all the way to the far left and just start hitting delete until you get to this part right here. So that's the 2.8453 multiplied by the standard error. Multiply those two together, and that's our margin of error. Let's round this one to 2 decimal places as well to reflect the width of the interval. It's 4.02 years. So for something as critical as early onset of dementia, that's a pretty wide margin of error. But now we have a good idea of what's going on in this clinical population for having early onset dementia as a diagnosis. Any last questions at all, folks? Getting the interval down or the margin of error? Okay, well, let's go to a conclusion to finalize the problem. It's basically saying you put this in the middle. Same sort of thing that we did in chapter 13, what you'll see on exam 3 next Monday. Only difference this time is it's quantitative data. It's a different kind of interval. The part E with what we're about to do should feel extremely similar to what you did in chapter 13. We first mentioned the level of confidence. It's at 99%. So we can say with 99% confidence, and you come out down here, we're thinking mu, but we can't write down mu itself. We have to give an interpretation that makes sense to everybody, and you're going to lose everybody. Well, a lot of people, the moment you start mentioning Greek letters. So we just say exactly what we said earlier, what mu really is. With 99% confidence, the population average age at diagnosis, we don't have to say in years because we'll say years when we go to write down the interval. Let's go and say for all people, diagnosed. If you said diagnosed with this condition, that's okay too, because you've already said clearly what the condition is at the start of the problem. But let's just be really specific. Diagnosed with early onset of dementia. So we said what mu is, then we just say what values it's between. Is between 48.51 and 56.54 years. Then that finalizes the problem. If this was indeed a random sample, hopefully a simple random sample of that population, then we can be very confident that this is an accurate result. Confidence level is also high as well. There's a chance that the parameter mu isn't actually in this interval, but after doing this study 100 times, only one of those 100 intervals would not capture the parameter mu the way this interval did. So that's what we mean by 99% confidence. We did it, folks. That's a pretty fast wrap up of a problem when you think about it. Once you have the parameter down, think through the context, the mechanics go the same exact way each and every time, just different data, different sample sizes. And the conclusion is just nailed down by what you said by part A. So all the questions go essentially the same way in chapters 13 to 14. We'll practice one more, example 5 next. Any last parting thoughts, questions, or comments before we change over to the next problem? Okay, so now we have a really good feel for what inferential statistics looks like. We'll practice more of these, one more problem like this one, and we'll be looking at a totally different kind of method, hypothesis testing in chapter 15. Hypothesis testing is really trying to address the same kind of questions that we've been answering, but looking at it from a slightly different perspective. And sometimes when you take an introductory class like this, the chapter 14 method with the confidence interval, and the hypothesis testing question feel like totally different procedures. That's just kind of a consequence of how the book is written, how the chapters go. In reality, these go together. Oftentimes when you do a statistical study, you write down the hypothesis test. If you get a critical result or not, you estimate the parameter through the confidence interval. So we're just looking at the other side of inferential statistics in chapter 15. So we'll be visiting that in just a moment after we do one more question here on these notes, chapter 14. Chapter 15 looks weird, but just keep in mind, we're really doing the other side of the same coin is what we're doing in fact. So here's our last question for confidence intervals. Starts off with just a reminder that calcium is important. It says, calcium is the most abundant mineral in the human body, has several important functions. We definitely know that's true. Most body calcium is stored in the bones and teeth, where it functions to support their structure, so more information. And usually the first sentence or paragraph here is just getting us all on the same page kind of context. The study seems to be about calcium based on what we see here. Now it gets interesting. Recommendations for calcium, and keep in mind this is not meant to be dietary advice for anyone. This is just a random statistics problem. So recommendations for calcium are provided in dietary references intakes developed by the Institute of Medicine of the National Academy of Sciences. So you could look this up to find these recommendations. The recommended adequate intake of calcium for adults. And this is nice. They define adults as aging between 19 and 50. So they're excluding the older geriatric population. Recommended adequate intake is 1,000 milligrams per day for calcium. So this is not really saying exactly what's going on in the problem. It's just more refined context, telling us more about what we're doing and giving us a value to think about. And this is now telling us what the study is actually doing, the one we're examining. We have a simple random sample of 18 adults. So that implies through the context, 18 people in that age range, 19 to 15. But it doesn't hurt to pen in, sample size n is 18 for the sake of the formulas. And this is interesting. With all 18 people in this random sample, we're told the incomes were below the poverty level. So that gives a little bit more interesting drama going on in this problem. We have a benchmark for what adequate intake is meant to be, 1,000 milligrams per day. But these are people who are struggling. They're both below the poverty level. And for this random sample of 18 adults, this is their daily calcium intake. Some of them are meeting the level quite a bit. Some of them are excelling. They have a 1313 milligrams per day. But some of them are on the pretty low end, like the 633. So these are people who are struggling potentially quite a lot more, or maybe struggling and making strange dietary choices at the same exact time. There's a lot that could be going on with these data, but we have statistics at least. If the statistics weren't provided, we would have had to import them into the calculator and crank them out like in the last problem. So I believe we're using green for the mean in this entire set of notes. Let me double check that. I don't want to flip the color coding. Okay, so blue for the standard deviation. And I'm looking at my units. I'm not completely satisfied with these. This is milligrams, but it should have been milligrams per day if you're being really specific here. So that might be a good thing to pen in as well, just as a quick little correction on the unit. Well, that's the entire statement of the context. First thing we want to write down to get this all started to support our end conclusion is what is the parameter? Well, we know the data is quantitative, so we'll say population. It's up to you if you say mean or average. I'll leave it always up to you. We said average on the last one, so let's go with mean this time. Population mean of something for all of something. Anyone have a good take on what the parameters should be on this one? Yeah, let's say population mean, daily calcium, let me spell that right, intake. So we've got the quantitative variable indicated here the moment we've said that. Now we have to fill out the population. Anyone have the next part, the population? Will be for all something. Yeah, absolutely. We could say for all adults, but I feel like for this problem, it would be a hard decision if that's a minus, say, 1 point out of 4, if we just said all adults. Because it really feels like the big thing about this study is we're looking into a special segment of the population below the poverty line. So let's say all adults. And notice you could have said all people aged 19 to 50, but we can leave that written into the context. Adults are defined here. You don't have to be hyper specific. So this would be a good shortcut to take here. Let's let the rest of the context carry what that means by adults. All adults below the poverty level. Let's also think about what's going on in this problem. We're told that guidance by this fancy institute, National Academy of Sciences, says the adequate intake of calcium should be 1,000 milligrams. The sample mean is 947.4 milligrams. It is below. But now we have to wonder, is it statistically significant that that's below? That's part of what a question a hypothesis test would address. It would just formalize that as a statement involving the parameter. It would do a test using the data that we have here, or we can resolve the same exact thing, the same exact hypothesis test question, just by the confidence interval. So this is really what's going on in the problem. Seeing the mean doesn't tell us straight out. We have evidence statistically that this population is below the daily recommended calcium intake of 1,000. The real question about this problem is this average statistically significantly below 1,000 milligrams per day? That's the real question. So we've often mentioned this almost as a mantra. The mean is never the whole story when it comes to data. There's error in estimating mu with y bar. The error could be big or small. And the last problem, it was gigantic. 4 years feels like a lot for that kind of context. We have to roll in the standard deviation to see, are we significantly actually below, or were we just slightly off 1,000 by sampling error itself? That could be a typical value, even if the true value of this mu is right around above 1,000. So that's what the rest of the problem is about, to see if we have evidence that this population really is statistically significantly, that's a lot to say, below 1,000 milligrams. To do that, we go to the standard error, the critical number T star, and build out the whole confidence interval. But any questions or comments at all, folks, with just getting the parameter down? Okay, so let's write out standard error next. We have kind of a feel for how this should go. If it says standard error for sample mean, then in symbols, it's just SE for standard error, Y bar for the sample mean. Take S, divide by square root of sample size N. We recorded N as 18 in this problem. So this turns into 172 divided by square root 18. Back to the calculator, 172, let me clear all that white noise off. 172 divided by, hit second power 2 for square root, and then 18. And we have a standard error to 4 decimal places, 40.5408. Next, we need the critical number T star. Here's where we should go a little bit slower, a little bit more careful, like on the other ones. There's always a kind of sequence to this. You take the confidence level, write it out as a decimal, now it's 0.99. Then, once you have that confidence as a decimal, you write out what the left tail area would be, or right tailed area, if your calculator can flip it to the right tail. Area equals 1 minus 0.99, divide by 2. So whatever this number comes out as, we just drop it in right here. Then we compute degrees of freedom, sample size minus 1. You might have just put df equals 17, and that'd be totally fine. Going by the formula way, it's 18 minus 1, so 17 either way you do it. And this all produces the T star value that we're hunting for. We should remind ourselves that this is inverse T distribution in the calculator. So now hit second vars, go back down to inverse T. Our confidence level is the same, so the calculator line 1 is already set up the way we want it to be. Degrees of freedom, we do change on this one, so now it's sample size 17. And even though there's lots to talk about when it came to T star, it was a whole new distribution, the student's T distribution. Really, it just boils down to this when you're using it, applying it in the confidence interval. So kind of nice in a way. This is something that you get really good practice in and start to internalize pretty quickly in just a few problems. T star on this one is large, 2.8982. Does that look all right to folks on getting that value so far? Okay, so if you can get that value on these kind of problems, on the upcoming quiz 10 problems, my lab statistics problems, you're in great shape for doing this problem on the final exam. I feel like part C is the tricky part. And if you ever get stuck on an exam and you just can't seem to get that T star out, I can't tell you how to do it on the calculator because it's part of the exam itself. My advice is just put something down. Just give it your best educated guess of what you think it might be. You'll notice these critical numbers are always kind of in the same range. There's another 2.8. When we flipped it to say 95% confidence, it was just above 1.96. So if anything goes wrong, just give the best educated guess. You might lose a couple points here, but you wouldn't get double dinged when you drop it down in the next step. So now that we have all that, we're on our way. The confidence interval is just a matter of writing down the formula, plugging in the information. It goes y bar plus or minus the T star that we just found, multiply by the standard error y bar we found in the prior step to the last one. So we were provided with y bar, 947.4 milligrams per day. Add, subtract T star, and that one was 2.8982. Finally, multiply it by standard error, 40.5408. I can already hear the calculators going. You'll probably get this before me. Standard thing is just now throw all of that into the calculator. And for 7.4, I'll do the minus version first. 2.8982, 40.5408. So my lower value, this is to 2 decimal places as well, is 829.91 milligrams per day. That's on the lower end. On the upper end, I've got, let's take a look. Flipping that to positive as usual, and we have above 1,000, 1,064.90 in milligrams per day. So we got it, folks. That's the entire confidence interval. I forgot to color code that, so I'll just slap it with a highlighter. We now not only know what mu represents, we said in part A, we cast a 99% confidence interval wide net to estimate it. Y bar was an estimate, and it looks concerning because that's below 1,000. But when we include the entire margin of error, the plus or minus the critical number times the standard error, we have a more honest estimate for the unknown parameter mu. On the low end, it's even more concerning. It's pretty low. But notice on the high end, it exceeds the value 1,000. Mu can be anywhere in this interval. It doesn't even have to be in it. 1% of the time we do this operation, mu is not contained in the interval we produce. It could be below, so the picture could be even worse, or it could be above. Nothing of our data is going to tell us where exactly it is in the interval or where it would be if it leaves the interval. We're just 99% confident it's somewhere inside here. And that takes us down to the practical interpretation and then a follow-up question, part F. There's a follow-up question like this one in the homework for chapter 14 as well. But really what part F is leading into is hypothesis testing is what part F is all about. Well, let's write down that conclusion. We can now say, see if we can reveal that statistic of parameter above with 99% confidence. We'll say the population mean daily calcium intake that part represents the quantitative variable that we're measuring in this study. For all adults below the poverty level, that's discussing now the relevant population that this study is all about. For all adults below the poverty level, so we mentioned mu, and we just say once again is between 89.91, 829.91 rather. I feel like I had to double check that. 829.91. You know, that's one of those weird errors where that's a rounding error, isn't it? That should have been 90. I would never take off a point for rounding, but MyLab Statistics does. That's why we're trying to be hyper specific with this each and every time we go to calculate it. So that would have been a really annoying one to make a mistake on. So double check the rounding on these, mainly for the homework. It's good to be accurate on quizzes and exams as well, but I'm never going to ding you for being off by 100th right there. So less between that value and 1064.90, I feel like this value is suspicious as well. Yeah, that rounded up with carry, milligrams per day. So that's the conclusion of the confidence interval analysis. The whole purpose of part E is now we have an estimate for this unknown parameter. Well, any last questions at all, folks? Finishing off this one. Okay, but there's more to this problem. Oftentimes, these studies aren't just about a confidence interval. A lot of statistical inference questions like these have something important we're trying to address, some other comparison we're trying to make. Not for every single problem. Some problems are really just about the estimate and nothing else. But this one seemed to have a lot to do with an overall question that's implied here. Is this population of people with incomes below the poverty level, or does this population have an average daily income? Sorry, I forgot how to talk. Does the population of all people with incomes below the poverty level have an average daily calcium intake level that's below the recommended level of 1,000? That's what this problem is really all about. And now that we have the confidence interval, we can address this. So let's put this on the next page. But first, let's think about this, because this is actually really kind of a tricky problem to answer. Anyone for yes or no? Anyone have a strong feeling about this one way or another? Sure. Sorry, go ahead.
I want to say no.
I agree with you on that, actually. No, because it goes above on one end, right?
You can't confirm where it's going to be, right?
Yeah, that's the whole idea of it. We don't know exactly where mu is. It's not in the dead center. Y bar is what's in the dead center for sure. That's all we can say about that. But there's uncertainty here. Let's imagine a slightly different scenario. So let's suppose this one went on the upper end, 957.83. So maybe it's a different random sample, just a different reality. But if both the lower bound and the upper bound is below 1,000, we had the same value here, 957.83, we would have said yes, we have significant statistical evidence that this population's average daily income calcium intake is below 1,000 milligrams per day, because our estimate includes only values below 1,000. But it's different this time. This is the tricky and confusing one. Our interval looks like this, goes 8 to 9.90, just on an ordinary number line, 1064.90. Just for emphasis on how this interval is built out, the sample mean y bar is directly in the center there. And the distance from here to here is the margin of error m that we computed on some of the other examples. It's the same distance going from here to here as well. But mu can be anywhere, like you were saying. It just happens to be here with 99% confidence. Mu is here with 99% confidence. All right, CONF for confidence, since I ran out of space. But the actual value that's been targeted in this question, below 1,000 milligrams per day on average, is a value inside this interval. Here is the 1,000 milligrams per day. Since it's inside our interval, and mu can be anywhere inside here with 99% confidence, it could in fact be in that region. It could be above 1,000. We don't have any certainty. I mean, if it's randomly anywhere inside here, overwhelmingly, it's more likely to be on this lower end. But the moment our interval includes values above 1,000 values, the answer to this whole question is no. And we can rewrite this whole question as a hypothesis test question in the next problem. It would be no as well. So we'll say here, just to finalize this problem, no, we do not have that significant statistical evidence because The confidence interval includes values above 1,000 milligrams per day. So it's entirely plausible if we really have a correct confidence interval for mu at 99% confidence, if mu is in that interval, it's plausible it's at 1,000 or larger. Again, it's a tricky question. Does that make sense on how we would answer this one? Thinking it through the lens of statistics? Okay. Essentially, the way we answered this question, like we've hinted at, is also the logic of hypothesis testing. But there's a lot to say in hypothesis testing. So our chapter 15, it is the last chapter of the semester. It's probably also one of the biggest ones. We're going to break it down very finely. The first section is just what are hypotheses and how to formulate them. Then we'll skip section 15.2 on type 1 errors, type 2 errors, which are a little bit more technical. We're kind of shy on time to cover that information. But we'll go into section 15.3, which is going to be hypothesis testing for categorical data. That's when we're dealing with p hat and p. Then the last section, 15.4, will be hypothesis testing for quantitative data. It's like redoing chapter 14 with mu and y bar, but now that it's formulated as a hypothesis test. So let's get into that section next. Any last questions or comments at the moment?
So if it was yes, we could just vice versa the language, right?
Yeah, you could say
Yes, we do have enough.
all values are below 1,000 in the confidence interval. Yeah, that would work out for that one. Other questions at the moment? Okay, well, let's take a look into the introduction to hypothesis testing. It's, full disclosure, a pretty tricky chapter to start. Once you get the idea of how it goes, it's just like confidence intervals. And the big takeaway as well is these things don't exist in isolation. Very often, if there's a hypothesis test, a confidence interval is also done in the same exact problem. Rarely you have just a confidence interval analysis, but hypothesis tests and confidence intervals very often go together. So think of this as kind of a fresh look into inferential statistics. We could have done this before confidence intervals, but it's a good chance to do it last because it feels like there's slightly more terminology, moving parts to think about. But really, it starts off the same way as confidence intervals would have started off. We talk about the major thing we're trying to estimate, a parameter. The parameter is a number that describes the entire population. We can estimate it with a statistic, but instead of doing a confidence interval analysis relative to that parameter, we can conduct a test of hypotheses. So first, here's the definition, and then a whole lot of white space, because the biggest thing we want to do is make this as concrete as possible with some relatable examples. First, it's the null hypothesis. The null hypothesis is denoted by this symbol, H sub 0, and this is read as H naught. Let's say that right away, just for reference. The null hypothesis written this way, H sub 0, read as H naught. Kind of mangled the spelling of naught. Not as just another way to say 0. So you could also just say H sub 0 or H0. Often it's just said H naught. The null hypothesis H naught is a claim about a parameter. And just keep in mind, when we were talking about parameters, main ones that have come up in this course are mu. That's our chapter 14, population mean. When it's quantitative data, the other ones that's come up is just lowercase p. That's a population. Proportion, or you could say percent. That's the one that came up in chapter 13. So the null hypothesis is some claim about either the population's mean or the population's proportion, either or. It's something that's initially assumed to be true, and that seems like a curious assumption, but it's kind of like a baseline. We assume that this is true right away, just to get started with the study. And then comes in the alternative hypothesis. This makes sense. The alternative hypothesis should be HA. But we often just read that as a HA. Null is another way to say zero, so that's why it's H sub zero or H naught. H sub A is a competing claim about the parameter. So those are the definitions so far. The null is an initial claim we assume to be as true. The alternative is the competing claim that we say about the same exact parameter, either mu or p. Let's think about that and kind of absorb it into our subconscious for the moment. Any questions at the moment with what we have for the definitions? Okay, if you've seen hypothesis testing before, you probably have heard of this analogy before, and it's a major one because the logic is completely and utterly identical. So if you like court TV, if you ever watched, say, I don't know what a good court TV show might be, Judge Judy, something like that, real court, actual law being practiced, the logic in a court of law is exactly this. In a court of law, the null hypothesis is a statement that the defendant is assumed to be not guilty. So let's write that out. This is a nice analogy because the logic is so familiar with what we know about the justice system in the United States that it helps us memorize this if we can just have some analogy to attach this to. So I'll write in a court of law, H naught is a statement that the defendant is not guilty. And what do we do in a court of law in the US justice system? We assume in the entire proceeding of that court, the defendant is in fact not guilty. It's taken as a direct logical assumption. So we'll say here, H naught is assumed true. But under the assumption that H naught is true, we start gathering evidence and say, well, how likely is this assumption? As evidence starts to pile to the contrary, that's what HA is trying to establish. This is essentially the job of the prosecuting attorney. That's our job as the statisticians. We are trying to show the alternative hypothesis is actually true. So HA, the alternative hypothesis, is the statement that the defendant is in fact guilty. That deserves an exclamation mark. So these are the hypotheses that we're going to think about using that analogy at court of law. And our job, let's write down this comment, as statisticians, you know, that's a hard word to spell, statisticians, is to show HA is true as a prosecutor. What will the actual prosecutor do? We'll use all sorts of evidence. Some of it might be witnesses. Some of it might be forensic. It could be hair samples, DNA samples, blood samples, could be fingerprint samples, all sorts of things. All sorts of things can be mustered together. But as us, as statisticians, what we'll use as evidence is sample data. So this is what hypothesis testing is all about. And you know, if we can establish the alternative hypothesis true, the next thing we'll want to do is estimate the parameter as well. That's just the confidence interval analysis. Even if we can't establish the alternative hypothesis is true, that's kind of a bummer because that's what the statistical study is all about. they will often still do a confidence interval analysis, estimating those parameters because it's still a curiosity. Why not estimate it even if you fail to show the alternative is true, is the thought. So if our job is to show the alternative hypothesis is true, here's another thing that's really wild about this. Let's imagine someone is really up in the court of law defending themselves, maybe some heinous crime. They could be put to death for this, something really, really serious. If they fail to find this person is guilty and court is done, court of law logically never proved the null hypothesis is true. We don't establish innocence in a court of law whatsoever. And this is the trickiest thing about hypothesis testing. No matter what happens in the conclusion of our study, whether we showed HA is true or we fail to show HA is true, we are never trying to establish a conclusion that the null hypothesis is true. You might have seen all sorts of drama in court TV about this as well. Someone who looks just guilty as all hell is let go, but that person's going to say to the media, my innocence was established probably, but that's absolutely incorrect. We just fail to establish guilt. We never establish innocence in a real court of law in the USA justice system. And it's the exact same concept in hypothesis testing. So as a big warning, we can never conclude HA, no matter how tempting, enticing it might be, we can never conclude HA is true. And this is verbatim the logic of the US justice system, which is carried over into hypothesis testing completely directly. What we need is a relatable example that ties us together, the parameters, the statistic, the data.
Mhm.
Yeah.
I thought you were saying we can never conclude that the null hypothesis.
Oh, yeah. Sorry about that. Good eye on that one. That should have been an H not an HA. Thanks for spotting that error there. We can never conclude the null itself is true. We never establish that the defendant is not guilty or innocent. Other questions about that so far? Like this needs a box at this point. Thanks for spotting that error.
Never conclude that it's true.
Correct, yes. The lights are flickering now, but other questions at the moment? Okay, well, let's tie this together with one big example. So this is something that could happen to you. Imagine you're summoned to traffic court, for example. And just so that no one feels called out, let's say for the null hypothesis, or just for the scenario first, and then the null hypothesis, Mike, me, is summoned to traffic court for speeding on a 35 miles per hour limit road on the way to work. So this is something that, I mean, it could happen. It's never happened before. I try not to speed. And the 35 mile per hour road, as I'm thinking, is the one on Anderson that crosses the two train tracks. You can imagine sometimes it's tempting to do 40 on that one. It's kind of slow doing a 35. What we need to actually form a real null hypothesis, a real alternative hypothesis, the actual H naught and HA, is an honest parameter now. So the parameter in this problem would be, well, it looks like it's quantitative data this time if we're talking about miles per hour, data with a unit. So if I'm summoned into traffic court, what they're going to be talking about is on average, maybe it's the average in the last week, maybe last semester, something like that. But we need a parameter down for statistics. Mu could be the population average speed on this road. Let's say in the last 12 weeks. So the whole semester so far. So maybe there's been like a traffic camera with a radar station on that's measured this, and someone finally took a look at it. They'll have data now. So if they took some random sampling of every time I went by on that road in the last 12 weeks, maybe we can compute a statistic like Y bar that estimates mu. But we also want to formulate these two sets of hypotheses. Mu is going to be the statement that, let's see here, the defendant is not guilty. What would that mean in this case? Mu equals 35 miles per hour. I'm doing the speed limit in that case. In other words, I'm not guilty. This could be written in a slightly different way. It could be written, or mu is less than or equal to 35 miles per hour. There's two ways to write this. Oftentimes it's written with a direct equality, sometimes with an inequality. So that's the statement. The defendant, me, is not guilty, but the state's or the county's prosecutor, whoever that might be, that's a person who's going to write the alternative hypothesis. The defendant is in fact guilty, and it would be a statement that goes like this. Mu is greater than 35 miles per hour. So that would be the alternative hypothesis. In traffic court, they're going to try to establish this. If they can find enough evidence, this will be the sample data using the statistic Y bar. Then, using the right distribution, either a normal distribution or a t distribution, they can say how reasonable is the null hypothesis in face of what the actual sample data looks like. What's the chance that this could be true given everything that we've sampled? So this is what a set of hypotheses could look like for that kind of scenario. Any questions about that so far? Okay, so this is the first part, just formulating those statement of hypotheses, thinking about what they're trying to do, what they look like, conclusions you can make, and conclusions you cannot make. We can never assume H naught, the null hypothesis, is in fact true. The next part of the notes is actually writing down all these kind of hypotheses for the different parameter values that we're going to see. First, it's always good to come back to this. There's only two conclusions we can ever give. Well, two things that can happen is, if we reject the null hypothesis, that means the prosecuting attorney found convincing evidence against the null. If H naught were true, the data would be very surprising. So we would reject the null hypothesis, conclude the alternative hypothesis is true. The other thing that can happen in our conclusion is we fail to reject the null hypothesis. Maybe the sample mean was above 35 miles per hour, but just like in that last problem with calcium, if you did a confidence interval analysis, if you looked at the data more carefully, it's a little bit more muddy. There's a large margin of error. So that's when we fail to reject the null hypothesis. But then the gargantuan caution about conclusions is just another reminder, even when we fail to reject H naught, we can never conclude H naught is true. And that's kind of unsatisfactory in a way. If I get summoned to traffic court for this kind of situation because of speeding, even if they can't establish the guilt that I was going above 35 miles per hour on average, I'm not exonerated. The court's never proved the null hypothesis is true. So if this was a more serious case, the moment you're summoned to court, it's as if your reputation is completely tarnished forever now, unless you find some direct, unequivocal proof that you must logically have been totally innocent. But the court of law is not trying to establish that either. And same with hypothesis testing. We fail to conclude the alternative is true. That means there's not convincing evidence against the null hypothesis. If the null hypothesis were true, the data is not surprising. But Statistics can't prove the truth of the null hypothesis whatsoever. So there's lots of things are frustrating about hypothesis testing. Lots of things are kind of exciting about it. And what happened in chapter 14 is essentially what we're talking about here. When we went down to this last part, way down below here, and found out that 1,000 milligrams was inside this interval, this is us failing to accept the null hypothesis whatsoever. So same kind of scenario happened on this one as well. We'll come back to this idea to tie it all together. But first, here's the peek on what the alternative hypotheses, null hypotheses are going to look like. There's three kind of different alternative hypotheses, and one overall null hypothesis, written with equality, sometimes with a less than or equals or a greater than or equals, but more often than not, with just a direct equality. There's lots to talk about with this kind of stuff, so we'll look at some examples, like example 1, just writing down the hypotheses, saying what the parameter is. We'll do the same with kind of a bigger one, example 2. And then we'll tie it together with what happened on this problem 14, chapter 14 example here. See what's going on with calcium. If we viewed it as a real hypothesis test, what would it look like? So 15.1 is just saying what the hypotheses are, how to write them down. Then when we go through the rest of chapter 15, it'll be about the mechanics. We'll be doing that after our third exam. But any last questions at all, folks? Just thinking about what hypothesis testing looks like, what it is.
Can you scroll down a little bit?
Yeah.
Where it says the hypothesized value, like the alternative, what would the hypothesized value be
I'm glad you asked about that.
in this? Well, I guess you could do the calcium one, sure.
In this one, it would have been 1,000 milligrams per day. That's the hypothesized value.
What about in the speeding example?
On the speeding example, hypothesized value would have been 35 miles per hour. That's what it would establish the innocence. So yeah, that's a great point to tie this together. This is the hypothesized value that it's mentioning in the notes there. And we've seen a lot of other weird kind of problems that talks about this as well. Let's look just at a moment at chapter 13. No, let me see, chapter 13.2. See the fan speed up on the, hear the fan speed up on the computer. It kind of does. Let's see here. Not quite 13.2, maybe 13.1. I have one interesting hypothesized value that I just wanted to mention as another takeaway. Let's see. Maybe it was 13.3. Sorry for the holding you for just a couple moments longer. Wasn't quite this one. Wasn't the infants.
The blood one?
It was the one about being drunk,
Oh,
where kids were drunk in a school setting. It's been a while, so it's got to be somewhere. I know we looked at a study with crazy kids. Oh, here it is. After hearing of the national result, 44% of students engage in binge drinking. University administrator surveyed a random sample of 244 students. 96 of them admitted to binge drinking. We wrote down a very specific parameter P for one population. And the hypothesized value, if we redid this as a hypothesis test, is 44%. So that's the hypothesized value on this one. We're hypothesizing that this university is different than the national value, that they have less people engaging in binge drinking. So we would be putting that together with a less than right here. The parameter would be P, and we put in the national value of 44% would be the hypothesized value that goes right here. So that would be the hypothesis test for that problem on that one. Just about each one of these problems that we looked into could be a hypothesis test in some way, shape, or form. But any last questions at all, folks, before we call it a night? Okay, we'll see how to carefully build all of these after taking the review questions tomorrow for exam 3, or more likely if we take a longer time with the review after the 3rd exam, so a week away from today. So we'll refresh some of this as we get back to it. But for now, have a great night, folks. I don't want to keep you too much longer. We're already a few seconds over.
See you on Thursday.
Yep, have a good one.
It's just makes me think of biology, how you can't like say a straight up answer in biology.
Yeah, it's pretty much what's going on. The sciences has this same defect as well. You can put down a confidence interval in biology, but you can never say mu is exactly this. So same thought here with the null hypothesis. You can never directly conclude the null is true either.
That helps my brain.
That's awesome. Have a good one.